I'm Hal Weber, and I'm a trainer for Eiffel Software. This presentation is the first installation of a multi-part overview of Design by Contract, Eiffel's facility that helps you build more reliable software. In a way, I'm kind of sorry that you're watching this presentation over the web rather than seeing it in person, because like most Eiffel programmers, I'm really passionate about this Design by Contract thing. So when I really get into it, my students tell me I jump up and down and my eyes bug out and I tend to foam at the mouth. Sounds pretty entertaining. But really, Design by Contract, DBC for short, is in my opinion one of the 4 or 5 best ideas ever in software engineering, and that's no exaggeration. It's right up there with information hiding, abstract data types, and of course relegating the go-to statement to a dusty shelf in the Museum of Software Antiquities. So let's get started. In this presentation you'll get a little background on reliability, and then we'll use an example to demonstrate how Design by Contract affects the way that you develop routines. Lastly, we'll see what it means for software to misbehave. Why are we here? The answer, of course, ultimately, is economics. When software fails, that costs us money. So we want to avoid software failures, and we do that by producing software that's reliable. And to do that, there's no better tool than Design by Contract. But our motivation doesn't really end here. Software failures are expensive, but software itself is expensive. So we want to develop as little as we need to and reuse as much as we can. Eiffel is a reuse-centric method, and arguably one of the most critical prerequisites for a successful program of software reuse is having something worthwhile to reuse. Design by Contract not only enhances reliability, but presents software modules to potential reuse consumers in such a way that the module's interfaces and semantics are both clear and unambiguous. And Design by Contract does even more. Stick with me and I'll summarize the benefits at the end of this overview. Let's talk a bit about what we mean when we use the term reliability, and then we'll get into a simple programming example. We see reliability as the combined effects of 2 software quality factors, correctness and robustness. What does it mean for software to be correct? Well, informally, we can say that correct software does what it's supposed to do. And if we want to be a bit more complete, we could say software that is correct does what it's supposed to do, and only that. For example, asking for a monthly statement from your online banking system should give you the statement, and it should do that without changing the balance in your account. Robustness means that in any cases in which software cannot do what it's supposed to do, it behaves in some acceptable fashion. Although these definitions seem pretty straightforward, there's one tricky part, and that's the what it is supposed to do part. There's an implication that we can express what our software is supposed to do, which in turn implies that we actually know what it's supposed to do. We call the specification of what software is supposed to do, oddly enough, a software specification. So we can view reliability only relative to the software specification. Correctness is a realm of behavior defined by the specification, and robustness covers how the software performs in situations that are outside of the specification. Specification then is vitally important to evaluating reliability. In fact, unless we can state what a software element is supposed to do, it's pointless to speak of its reliability. Okay, now with that in mind, let's consider this multiple choice question. How do engineers express what software is supposed to do? Well, if there's a right answer, it's probably D. But really what I want you to see here is that most software specifiers can be classified into 2 camps without much middle ground, the B camp and the C camp. And it turns out that neither choice is very good for mainstream software engineers or the software itself. The great majority of engineers who attempt to specify software at all fall into the B camp. That is, they attempt to write down in natural language a description of the semantics of the software, and that ordinarily works only marginally well. Much research has shown that natural language specifications are often incomplete and fraught with noise, ambiguity, and contradiction. So typically, natural language doesn't give us a very good specification. And because of the problems with natural language, the people of the C camp arise and turn to the most complete, unambiguous language they know, mathematics. Formal specifications are written in notations with names like Z, Larch, and VDM, systems that are based on discrete mathematics. Although they may produce very precise specifications, most software engineers, managers, and domain experts don't have the mathematical backgrounds to use these tools. It's probably no exaggeration that formal methods in software specification have produced many more PhDs in computer science than they have reliable software systems. And there's one more problem shared by both camps: document synchronization. So you produce a really good specification, that's one document, and then you produce software from that specification, that's another document. That means that constantly you must take special care to ensure that the running software always reflects what's in its specification. So neither B nor C by itself is a solution without significant problems. But that doesn't mean they're not based on some good ideas. The correctness model in design by contract is based on an idea that came from the application of mathematics to the study of software. But the great thing about design by contract is that we don't have to be mathematicians to reap its benefits, a fact that personally I find comforting. Although its effects are far-reaching, this model itself is really pretty straightforward and simple. Informally, it goes like this. For any software routine, we should be able to make a statement of all the conditions that must be true in order for the routine to work correctly. This statement we call a precondition. Then we make a statement of all the conditions that will be true if indeed the routine worked correctly. This statement is the postcondition. The routine works correctly only if the precondition and postcondition are met. Now we're ready to see an example. Imagine that we're going to develop a class called time of day. At runtime, each object that's an instance of time of day will represent some valid time of day accurate to the second. So valid values for time of day would range from midnight until 1 second before midnight. We might specify some queries to be implemented in the time of day class, like hour, minute, and second. Remember, queries are questions that we can ask about instances. So if some instance represented 7:30 and we applied the query minute, we'd get back 30. Then we might define a query isBefore that we could apply to a time of day and provide a second time of day as an argument. IsBefore would return true if the target instance represented an earlier time of day than the argument. With commands, we specify some action to be taken by an instance of time of day. For example, if we call setHour on an instance and provide an integer as the argument, then the instance's hour should be changed to the integer we provide. Of course, there could be other features of the time of day class, but these are enough to illustrate the effect that design by contract has on routines. What we're going to do next is to take an in-depth look at the routine setHour. But first, let's consider an implementation decision that we would have to make as producers of the time of day class. If each instance of time of day is to represent a valid time of day, then we have to make a decision about how we're going to keep the time of day information within the states of the instances. Possibly the most intuitive way to do it would be to keep 3 integer attributes called hour, minute, and second to represent the hour, minute, and second for any instance. This would work well for our queries, hour, minute, and second, because they would be accessible directly by client code. But it would complicate matters for implementing isBefore that compares 2 times of day. We'd have to do some computation to compare 2 instances. But we wouldn't have to use 3 integers to keep the time of day internally. We could use only 1 integer attribute called, say, second since midnight. It would keep the time of day as the number of seconds since the day began. This would make it very easy to compare 2 times as in isBefore, but it would mean that hour, minute, and second would probably be implemented as integer functions rather than attributes, because their values would have to be derived from seconds since midnight. So the value for the query hour, for example, would be computed each time it was called for. You can see there are pros and cons for either option. But for the time being, let's use implementation option 1, 3 integer attributes representing hour, minute, and second. Now that we've made that decision, let's see how we would implement the procedure setHour. Well, it doesn't appear to be too complex. We simply accept the argument from the caller and make the assignment to the attribute hour. So the code in a class which is a client to time of day could look like this. First, here's a declaration of an attribute called coffee time of type time of day. Then sometime later in some routine of the class, we see setHour being used to set the hour for coffee time to the integer value 10. And that works fine. But what if the developer of the client class codes this? What would setHour do? Well, nothing good for sure. setHour would go ahead and do what it did before, and we'd end up with coffee time at 118 o'clock. And we know that's not valid. In the days before Design by Contract, we were taught to do defensive programming. So as soon as a routine was entered, we would code a bunch of ifs that would validate the arguments. DBC frees us from that sort of thing. Let's revisit our model for correctness. Okay, here we go. For any routine, in this case setHour, we state the conditions that must be true in order for the routine to work correctly. In this case, that means that the integer h passed by the calling client must be between 0 and 23 inclusive. So that's the precondition for setHour. Now we state the conditions that will be true upon the routine's successful completion. Well, if we ask the instance for its hour, then that number will have to be the same as the argument h. So that's the postcondition. Next, we'll see how in Eiffel we can express these conditions directly in the routine itself. The require keyword introduces our precondition. The ensure keyword introduces our postcondition. And usually we put a name tag on each assertion clause just in case we need to look it up later. At this point, there's just one more thing we need to specify about setHour. Remember that we said in the beginning that correct software does what it's supposed to do, and that's all. So we want to make sure that what we did to change the hour doesn't have any effect on minute and second. The keyword old allows us to access the value of a query as it was before the execution of a routine. So these two lines ensure that the values for minute and second after setHour executes are the same as they were before. Now, when I teach this in a classroom, usually about now, somebody says, wait a minute, maybe I'm willing to buy this part about validating the age. But checking the hour seems totally unnecessary in this case because anyone can see that the only thing the routine does is set the hour. So this business of checking minute and second seems superfluous too. Okay, I'm glad you mentioned that. I think it's a natural reaction. I had it too. In order to begin to clear things up for you, let's look at another view of the routine. This is the contract view of setHour. It contains the call signature, the header comment, and the pre and post conditions. But importantly, it leaves out the implementation. Eiffel is a reuse-oriented method, and this view is how any potential reuser of class time of day would view the setHour command. It's the specification of setHour. That is, it states what setHour does without saying how it does it. And it defines a contract between setHour and all potential reuse consumers of time of day. The contract says, if you want to call setHour, then you need to provide an integer h that ranges in value between 0 and 23 inclusive. And if you do that, then I guarantee that when I'm done, A, you can ask for the hour, and its value will be the same as the h you gave me, and B, that I'll leave minute and second unchanged. So each routine in a class gets a specification like this, which reusers see as its contract. Now back to your question. Remember at first we looked at two implementation options for time of day. We chose option 1. Imagine now that we had chosen option 2 instead. we'd keep the time of day internally in each instance as one integer attribute, which is the number of seconds since midnight. So the query's hour, minute, and second would not be integer attributes. Instead, they'd be integer functions which compute their respective values each time they're called. Let's consider the effect of choosing option 2 on the procedure set hour. First, how does this change the stuff between the do and the ensure? Well, it complicates it considerably, right? There's no longer an hour attribute to assign to. Now what we have to do is to make the right change to seconds since midnight to make the hour come out right. So what would an implementation of set hour under option 2 look like? Well, we can imagine a possibility. Maybe first we convert the old hour and the new h both to seconds. And then from seconds since midnight, we would subtract out the old hour expressed as seconds and then add back in the new value h expressed as seconds. But the important thing to understand is that our state attribute, seconds since midnight, will have to be changed through some computation that will be more complex than just assigning to hour as in option 1. Okay, now consider the contract view of set hour. What's the effect of implementation option 2 here? Well, the answer is no effect at all. So how set hour does its work changes considerably, but what it does, that is its specification and its contract with its clients, does not change. Now once we've implemented option 2 with that ugly computation, the hour set assertion clause isn't just an echo of the implementation anymore. And since with option 2 we're manipulating seconds since midnight, from which hour, minute, and second are all derived, you can see that there's a lot more chance that in implementing set hour we may cause some collateral damage to minute or second. This illustrates that this specification, this contract, is, in a sense, independent from its implementation. They're two different things with different purposes. The specification is what it is, regardless of whether the implementation is trivial or complex. And that brings up another point. Maybe you've already recognized that in this example, I've gone about things sort of backwards. First, I implemented the routine, and then I added the contract. I did that because in the absence of DBC, routines are implemented and then shored up with defensive programming. But that's not the way Eiffel programmers do it. What you see here, the contract, is what an Eiffel programmer would construct first. Once we have a good feel for what our software must do, then we decide on the most appropriate implementation. Okay, just one more thing and then we'll move on. If you viewed the Eiffel overview, then you were introduced to a design principle called command query separation. Also, you heard me promise to give you the reason for command query separation in the design by contract presentation. Well, here it is. Command query separation says that any routine should be a command or a query, but not a mixture of the two. This means that any routine that alters the state of an object should not return a value, and any routine that returns a value should not change its target object. In Eiffel, that means that only procedures are used to do the types of computation that can change the state of an object. Functions should never do that. The simplest way to think of it is this. A query is a way of asking a question about an object, and the process of answering a question should not change the object. The reason for command query separation is this. It is impossible for us to reason about the correctness of the state of an object by using queries that change the object. You see, we use the queries, attributes, and functions to construct our preconditioned and postconditions. If one of the functions were to change the object, then the result would no longer be valid. Set hour is a procedure, and indeed it does change the state of a time of day object, either by changing hour in implementation 1, or by changing seconds since midnight in option 2. We use the queries hour, minute, and second to ensure that set hour has worked right. In option 2, these queries are implemented as functions. If one of these functions changes the object in the process of giving us an answer, then the answer cannot be relied upon. A contract between software elements is really a lot like a contract between human beings. Each party has obligations to fulfill and benefits to reap. In the case of software contracts, those obligations and benefits are evidenced by the precondition and postcondition of the routine that's supplying the service. In our example from class time of day, the routine set hour is supplying an update service for clients on an instance of time of day. The client's obligations come from set hour's precondition. The client must provide an integer argument h that's within the valid range. In return, the client benefits by having the instance updated as stated in the postcondition. The supplier's obligation is, of course, to update the instance properly, as stated in the postcondition. But the supplier benefits as well. Because the precondition specifies valid criteria for the passed argument, the supplier code never has to be defensive. If set hour ever executes, it executes with a valid h. There's another way that software contracts are like contracts between human beings. They can be broken. And they can be broken due to either party not meeting its obligations. So what does it mean for a software contract to be violated? Well, because the contract is the software specification, it means that the software is not doing what it's supposed to do. And that means, quite simply, that the software is not correct. It contains a bug. So let's see what happens to a running system when a contract is violated. Now we come to one of the most valuable benefits of design by contract. Because we have the contract, we don't have to do any guesswork about which pieces of code we need to protect with try structures, as in C++, Java, and C#. With DBC, the rules of execution are clear, simple, and global. They go like this. Every call to a routine can complete in one of only two ways. Either the routine's contract is fulfilled, or it is not fulfilled. That's simple enough, but there's a little bit more. If a call causes a routine's contract to be violated, then this, in turn, will always cause the caller to deal with an exception. So what it boils down to is this. At runtime, when software goes out of spec, that is, when a bug manifests itself, an exception occurs. So what can the caller do about it? Again, there are only two choices. A routine suffering an exception can either 1. Ensure that the object is in a valid or stable state and retry the routine, or 2. It can fail itself. Now a couple of notes on the first alternative. First, when we say that the routine returns the object to a valid state, that has specific meaning, and we'll discuss that in the next DBC installment. And the other thing is that the routine may retry using the same or possibly some alternative strategy that it keeps for just such occurrences. One reason this is so valuable is that it bases the whole business of exceptions on the specification of the running software. It doesn't allow us programmers to abdicate our responsibility. It says if something goes wrong, you've got an opportunity to recover. Either you can recover or you can fail, but you can't ignore it. Well, that wraps up the first installation of the Design by Contract overview. We hope you found it interesting, and we hope that you're intrigued enough to follow through to the next episode. We'll finish the full definition for the contract of a class. We'll talk about what happens to inheritance in the presence of contracts. And we'll summarize the benefits of Design by Contract. I hope you'll join me